Hey loyal fans! In this video, I explained the current scientific thinking about how the universe began. I'll start by explaining a few essential things you need to know to understand the theory. To get into the right mental state, I ask that you watch this video while you're rested and in a quiet, contemplative state of mind. I ask this because the ideas I present require an intellectual stretch, not because they're overly complex, but because they take you far from everyday life. In the first section, I describe some simple physical principles like mass, energy, and gravitation, and a basic rule about mass energy that everyone needs to know, a rule nature never breaks. To set the mood, let's travel away from Earth on an imaginary spacecraft, drift among the stars, and think about a much simpler reality governed by a handful of simple and consistent mathematical principles, far from earthly struggles, far from doom scrolling, from the evening news, from "I told you so," and "what will they think of next?" Okay, loyal fans, I hope you're ready for an adventure. Let's get started. Mass and energy are aspects of the same thing, something called mass energy. When you fully charge an electric car with a 100 kilowatt-hour battery, the car gains 4 micrograms of mass. A 10 megaton nuclear weapon converts 466 grams of mass, roughly a pound for non-metric people, into energy. Now for rule number 1. Mass energy is never created nor destroyed, only changed in form. This rule wasn't even broken during the Big Bang, the moment when the universe came into existence, as I will explain later in this video. We can test these ideas by examining an elliptical orbit, one in which a satellite constantly changes distance from the orbited planet. In this kind of orbit, a satellite changes distance from the planet while speeding up and slowing down. The satellite's distance from the planet represents potential energy, PE, while its speed represents kinetic energy, KE. In this elliptical orbit, notice that the total orbital energy, PE plus KE, remains constant, even as the kinetic energy, KE, represented by motion, and potential energy, PE, represented by position, are changing. This orbit demonstrates rule number 1, energy can only change in form. Because the satellite is moving through a vacuum, meaning it's not losing any energy to heat or collisions, so its total energy must remain constant. Notice about the potential energy, PE, display at the upper left. It's always negative. That would mean gravitational energy is negative. Is this real? Or is it just a lazy trick by physicists to make the numbers come out right? Well, it's real. Gravitational energy is negative. Here's the reasoning. Item 1. 2 masses with infinite separation should have a gravitational energy of 0. Item 2. 2 masses moving together should show a decreasing gravitational energy, thus descending below 0. Item 3. 2 masses moving apart should show an increasing gravitational energy, thus ascending towards 0. To satisfy points 1 through 3, gravitational energy must be negative. Okay, that was a bit complicated, but it's key to our understanding of the universe's creation. Just remember going forward that gravitation is negative. Let's now explore different kinds of orbits and how they relate to energy. When masses move together and apart, they tell us about the universe, and they serve to either confirm or falsify our physical theories. Here's a chart that shows the 3 classic orbits: elliptical, each with a negative net energy; parabolic, just one with a net energy of 0; and hyperbolic, each with a positive net energy. Let me add that a circular orbit is an elliptical orbit with an eccentricity of 0. If it's exactly circular, it shows all constant values, constant velocity and altitude, and constant energies. Notice that this orbit's potential energy is exactly twice its kinetic energy, but negative. Because it's gravitational energy, of course, it's negative. Elliptical orbits all eventually return to the parent body, even if this requires centuries, as sometimes happens with solar system comets. These orbits demonstrate energy conservation, both in simulators like this and in astronomical observations. If an elliptical orbit should lose energy over time, this must result from a source of friction that converts some of the orbit's energy. For example, if an elliptical orbit dips into a planetary atmosphere, atmospheric friction can harvest the orbit's energy, and the body may eventually crash into the planet. Hyperbolic orbits, paths, have positive net energy, so they depart the parent body and never return. This is a desirable energy level for an interplanetary or interstellar mission. For example, survey craft like the Voyager 1 and 2 spacecraft, now leaving the solar system. But for me, the most interesting orbital path is parabolic, and for a given planetary mass and altitude, there is only one such orbit, with only one outcome. A parabolic path, not strictly speaking an orbit, is defined as having zero net energy, the sum of potential and kinetic energy, at each point along its journey. The craft gradually slows down over an infinite time and distance, and as it approaches an infinite distance, its kinetic and potential energies independently converge on zero. I'm going on about this because a zero-energy parabolic path is critical to explaining what happens at the Big Bang, so please remember this point for later. A digression. I must add a comment about infinity, one of my favorite topics. Notice I earlier said that the orbiting body approaches infinity. I put it this way to avoid claiming that the body gets to infinity, which makes no sense. Infinity is not a number, it's an idea. Infinity is not a place, it's a concept. I regularly hear calculus students say about a limit expression that when x equals infinity, then 1 over x equals 0. But that's not what a limit expression means. Limits only approach their targets. They can't arrive at infinity any more than a spacecraft can arrive there. It's well understood that quantum and relativity theories are incompatible. But as it happens, both play a part in our current ideas about the birth of the universe. This section describes a theoretical synthesis that joins quantum and relativity theories in the fate of black holes. Relativity theory explains things at the largest scales: planets, stellar systems, galaxies. Quantum theory explains things at the very smallest scales, dimensions smaller than an atom. In relativity theory, an object either exists or it doesn't, and things move about in slow and deliberate paths. In quantum theory, by contrast, ghostly entities called virtual particles appear and disappear in seemingly random ways, but while obeying the all-important rule number 1 stated earlier: mass energy can only be changed in form. But these virtual particles, which always appear in pairs, can affect the macroscopic world in unexpected ways. One surprising effect is their interaction with black holes. A black hole is a superdense object from which even light cannot escape. At least, that was the original theory. It was once thought that mass energy could only fall into a black hole, making it more massive over time, but nothing could get out. We now know this is not true. In 1974, physicist Stephen Hawking and others realized that under particular circumstances, virtual particles could extract energy from a black hole. This effect, now known as Hawking radiation, results from virtual particle pair creation near a black hole's event horizon. The fate of the two particles can differ, which creates a net radiation of energy from the event horizon. In my quantum particle pair animations, I show one particle crossing an event horizon while the other escapes into normal spacetime, but this is just a convenient visualization, not a literal description. If a black hole is located in a place where it doesn't absorb sufficient mass energy from its surroundings, the Hawking radiation effect will eventually cause it to evaporate. This outcome is more likely for small black holes than for large ones, because of a sphere's cube versus square ratio of volume to surface area. The discovery of Hawking radiation resolves a long-standing mystery in cosmology. Many small black holes should have been created in the high-energy conditions of the early universe, but there are no small black holes at present. It turns out that over the lifetime of the universe, Hawking radiation evaporated all the small black holes. And a good thing too, because if those primordial small black holes still existed, they would make life impossible. This means quantum effects, apart from making computers possible, also make us possible. I include this section about black holes and Hawking radiation primarily to show that virtual particles, once thought to be pure theoretical constructs with no effect on the macroscopic world, are now known to have a number of large-scale effects. It's also important to say there's no theoretical barrier between the microscopic quantum realm and the macroscopic world we live in. Large-scale quantum effects aren't forbidden, only improbable, and that probability can be calculated. And as physicist Murray Gell-Mann once said, everything not forbidden is compulsory. This section uses the information presented earlier to explain how the universe came into existence, without breaking rule number 1, without violating mass-energy conservation. But first, here's an eye-candy Big Bang. This VR simulation correctly shows declining temperature over time, but has the accuracy drawback that since there was nothing outside the Big Bang itself, no time, no space, the camera viewpoint didn't exist in reality. People may fairly ask, how can an entire universe of mass energy come into existence without breaking rule number 1? Well, according to current thinking, the universe's expanding mass energy had the exact velocity profile described earlier for a zero-energy parabolic orbit. So the net energy of the universe was, and is, 0. Someone might say, okay, microscopic virtual particles appear and disappear all the time, but quantum fluctuations can't happen on a large scale, can they? The answer is that a quantum fluctuation can happen at any scale, but with decreasing probability as the scale increases. Bigger fluctuations have a smaller probability. For a fluctuation like the universe, we might have to wait 13 billion years. This is a science video, and science requires evidence as well as theory. Is there evidence for the Big Bang? Well, yes. The first clue was the discovery in the 1920s that the universe was expanding in all directions, which implied that at some time in the past, it must have been a dimensionless point. The second clue was the discovery in the 1960s of the cosmic microwave background radiation, or CMB. The CMB represents an afterglow of the Big Bang's originally high temperature, but spread out over the much larger present universe, so its energy density and temperature have greatly declined. Another way to say this is the original short wavelengths of the Big Bang thermal radiation have been stretched out by expanding space. Cosmologists who favored a steady-state universe argued against the Big Bang theory. In fact, the name Big Bang was coined by a critic to ridicule the idea. But discovery of the cosmic microwave background radiation is one of the strongest arguments for the Big Bang. The universe's expansion could be made compatible with a steady-state theory, but the cosmic microwave background is much harder to explain. The third clue is evidence for a zero-energy universe, which we find by measuring the curvature of spacetime. It turns out that the zero-energy model creates a universe with zero curvature at the largest scales. Local spacetime curvature is everywhere. For example, you're attracted to the floor by Earth's local spacetime curvature. But large-scale curvature has been measured and supports the idea that the universe has zero net curvature. A number of common myths exist about the universe. One is that the Big Bang took place in a pre-existing space and time. But the Big Bang created 3 space dimensions and 1 time dimension, altogether 4 dimensions called spacetime, along with all the mass energy contained within it. What may have existed prior to or outside the Big Bang is also outside the realm of science. Another belief is that the universe has a unique center. This isn't so. In fact, all locations in the universe emanated from a single dimensionless point. One example that may help convey this idea is to imagine a spherical surface that grows from a single point. Which point on the sphere's surface is the center? As to the popular multiverse idea, the problem is not that the idea may have merit, but that the issue cannot be resolved scientifically. Remember, science requires both theory and evidence. If we only have theories without evidence, it's religion, not science. If instead we only have evidence without theories, it's stamp collecting. So, according to current thinking, the universe came into existence because of a chance quantum fluctuation, not because of some grand plan hatched by a superbeing, as so many believe. This doesn't argue that God isn't real. Actually, nothing can do that. But it does argue that God isn't necessary. What does this mean? It means you're living in a universe that began by chance, and your own life also began by chance. This means you're free to invent a meaning for your life, choose your own goals and preferences, free to reject other people's beliefs about what you should do with your life. You have many rights and only one constraint: to avoid interfering with other people's rights. Thanks for watching this video. If you enjoyed it, please like and subscribe to my channel so others can learn how the universe was created.